In this video, I'm going to discuss about Euclidean lemma and Euclidean division algorithm to find the GCD of two numbers. First, let us look at Euclidean lemma. If A divides BC, where the GCD of A and B is equal to 1, then A must divide C. If A, B, C are the integers, and if A divides BC and A and B are relatively prime, then A must divide C. Let us prove this. It's given that A and B are relatively prime, so for some integers x and y, I can write 1 equal to ax plus by. Now I'll multiply this whole equation by c. Now I'm getting c equal to acx plus bcy. And it is also mentioned that a divides bc, right? A divides bc. So for some integer k, I can write BC equal to AK, and I'll substitute this in this equation so that equation 1 becomes C equal to ACX. In place of BC, I'm putting AK. AKY. This means I can take A outside, so that I'm getting Cx plus Ky. I'm writing C in terms of A into some value. Anything it can be, I'll take it as capital X or capital Y, something like that. I'm writing C in terms of product of A into something, right? Therefore, it just implies that A divides C. That is what we have to prove. Theorem says for the integers A and B, not both of them are 0. For any positive integer D being a GCD of A and B, that can be GCD of A and B if and only if D divides A and D divides B. Whenever C divides A and C divides B, then C must divide D. I have to take D as a GCD of A and B, and then we have to prove these two conditions. Second part is I have to take up these two and have to prove this D becomes a GCD. Okay. First part, let us take suppose D is a GCD of A and B, then D must divide A and D must divide B by definition. So I can write this GCD D as a linear combination of A and B as AX plus BY for some integers X and Y. Right. This if C is any divisor of A and B, if C divides A and C divides B, then C must divide AX plus BY, right? C must divide AX plus BY. What is AX plus BY? It is nothing but D. So C must divide D. Okay, so our first part is over now. If D is the GCD of A and B, then by definition D must divide A and B. If I write the GCD in terms of AX plus BY, and for any common divisor, say arbitrary common divisor C, if that divides A and B, then it must divide AX plus BY so that it divides the divisor D. So first part is over. Let us take the second part, converse part. Let d be any positive integer such that d divides a and d divides b. Then given any common divisor c of a and b, we have c divides d, right? Given any common divisor c of a and b, we will have c divides d. Okay, by that c must be less than or equal to d. That implies d is the greatest common divisor. See, I am taking any arbitrary common divisor of a and b, and that common divisor divides d, therefore c must be less than or equal to d. It implies d is the greatest common divisor of a and b. That is same as writing GCD of a and b is equal to d. Now let us look at few problems based on this. Suppose GCD of a and b is equal to 1, then prove that GCD of a square b square is equal to 1. So it is mentioned GCD of a and b is 1. So for some integers x and y, I can write ax plus by equal to 1. For some integer x and y, I can write ax plus by equal to 1. Now I'll take the square on the both sides, squaring both sides. I'm going to get a square x square plus 2abxy plus b square y square equal to 1. What I do is I'll multiply this equation. Equation 1 is multiplied by ax. Okay, I'm going to multiply equation 1 by ax. I'm going to get the equation a square into ax cube plus 2a square bx square y plus b square ax y square plus ax. Okay, sorry, this is equal to ax. After multiplying this equation by ax, I'm going to get this. I'll write this as equation 2. Now what I do is, for the same equation, I'm going to multiply by by. I'm going to get a square byx square plus 2ab square xy square plus b square into by cube, which is equal to by. This is equation 3. What I do is I'll just add up these two equations. Can add it, equation 1 plus equation 2. Can write a square in common, a square into ax cube plus 2bx square y plus byx square plus b square into ax y square plus 2ax y square plus by cube, which is equal to ax plus by. Now if I take this whole expression as another integer, say capital X, this whole as capital Y, and I know ax plus by is equal to 1, therefore I can rewrite this as a square into x plus b square into y equal to 1. A square x plus b square y equal to 1. It means that GCD of a square b square is equal to 1. A square b square equal to 1. This is one way of proving this. You can even prove it like by taking GCD of a and b equal to 1, and you rewrite this expression by into 1 and replace 1 by ax plus by, and you can proceed like that, so that you will end up with GCD of ab square equal to 1. And similarly you can even prove GCD of a square b equal to 1. So that from these two expressions you can directly write GCD of a square b square equal to 1. If you want, I'll just mention the other way of proving this. You have to prove GCD of a square b square equal to 1, right? So before proving this, try to prove this GCD of ab square equal to 1, which is same as writing GCD of b square a square b. Okay, if you can prove this, then from these two you can write this. I'll just mention you how to prove. Okay, so it's mentioned GCD of a and b equal to 1, so you can write for some integers x and y, you can write ax plus by equal to 1, right? Now in this place, ax plus 1 into by equal to 1, if I write it like this, then ax plus this 1 can be replaced by this, so ax plus by into by equal to 1. Proceed, ax plus ax by plus b square y square equal to 1, same as writing a into x plus bxy plus b square into y square equal to 1, which is nothing but just implies this one can be written a into something plus b square into something, so I can write a and b square are relatively prime. Similarly, you can prove GCD of a square b equal to 1. So from these two you can write GCD of a square b square equal to 1. This is the other way of proving. Next problem is prove that for a positive integer n and any integer a, GCD of a and a plus n divides n, and if that is the case, then GCD of a and a plus 1 is 1. It is mentioned a is any integer, okay, and any positive integer in fact, and n is a is any integer and n is any positive integer. So I can say a plus n is also an integer if GCD of a and a plus n, let me take it as say d. If this is the case, then d divides a and D divides A plus N, right? So I can write D divides A plus N minus A, which is nothing but D divides N. Hence I can write GCD of A plus N, that is D divides N for every positive integer, N. It says if it divides N, then GCD of A plus 1 is 1. Say suppose GCD of if GCD of A plus 1 is T, then T divides A and T divides A plus 1. Therefore, I can write T divides A plus 1 minus A. Hence, I can directly write T divides 1, which implies T is less than or equal to 1. That implies T is equal to 1. Therefore, I can say GCD of A plus 1 is 1. In the sense they are relatively prime. Now let us go for Euclidean algorithm. When two numbers are given, we can write their common divisors and we can find the largest one in the list and we can find the GCD. That is quite difficult when large numbers are given to you, right? So we have to find a more efficient way of finding the GCD of two numbers. That can be done by the division algorithm, and it's given by Euclid and it is described as follows. Say let A and B are two integers and GCD of A and B is desired. Okay, so we know GCD of mod A and mod B, this is same as GCD of A and B, right? So we assume that A is greater than or equal to B and it is greater than 0. And we apply division algorithm to A and B. Okay, applying division algorithm to A and B. How we write? A equal to some Q times B, or I can write Q1 B plus remainder R1. And this remainder is greater than or equal to 0 and of course it must be less than B. If this remainder itself is 0, then GCD of A and B is Q1, right? If the remainder is 0, if R1 is 0, then GCD of A and B is B, right? If this is not 0, if R1 is not 0, then divide B by R1 to produce the integers Q2 and R2 in such a way that, let me write, then divide B by R1 to produce the integers Q2 and R2 in such a way that B equal to Q2 R1 plus R2, and thus R2 is of course greater than or equal to 0 and it must be less than R1. Now let's look at this R2, whether it is 0 or not. Have to check. If this is 0, then the GCD will be R1. If this is not 0, then again write R1 in terms of Q3, R3, like that. You continue the process until you get the last remainder as 0. Okay. Just the last non-zero remainder will be the GCD. I'll explain this with an example later so that it is very easy to understand. Now let us prove a lemma. If A equal to QB plus R, then GCD of A and B is same as GCD of B and R. If I take D as the GCD of A and B, then by definition D divides A and D divides B. Therefore, I can write D divides A minus QB or BQ. I can write it anyway, no problem. Then D divides, what is A minus BQ? A minus BQ is R. So D divides R. This implies D is the common divisor of B and R. Now I have to show that D is equal to GCD of B and R. For that I have to show, I have to take up one more common divisor. Say let me take any arbitrary common divisor as say C. If C is an arbitrary common divisor of B and R, then this C divides BQ plus R, which is nothing but A. In fact, if it's a common divisor of B and R, then it divides, C divides B, C divides R. C divides B can be written as, say for C divides B and C divides R. If it's a common divisor, then C divides B and C divides R. When C divides B, C must divide, say, some BQ. C divides BQ and C divides R for some integer Q. Then I can write C divides BQ plus R. BQ plus R is nothing but A. Therefore, C divides A. This now C divides A, C divides B. Therefore, I can write C is the common divisor of A and B. Then D is also a common divisor, and I have taken D as a GCD of A and B. Therefore, this C must be less than or equal to D, right? Therefore, GCD of B and R is D, okay, and which is nothing but the GCD of A and B. Hence the proof. I'll explain this by taking an example. Suppose you have to find the GCD of, say, 143 and 227. Okay, you can list out all the divisors of 143 and 227. You can list out the common divisors, and among the common divisors you choose the greatest one, larger one, so that will be the GCD. But it is time consuming, therefore we are going by Euclidean algorithm. What we do is we try to write the largest number among the integers. Okay, in terms of a equal to bq plus r, in the sense I'm writing this, I'm taking this as a and this as b. I have to find r when I divide a by b. So this will be 1 into 143 once plus 84. If you want, you can do it by the procedure. Once like this you can write, and I'm writing 227 like this. Now take up this b. Okay, 143. I have to write product of r plus some other remainder. Okay, say once, only once I can multiply, and I'll get the remainder as 59. Then you rewrite 84 1 into 59 plus 25. Then you write this 59b as 2 into 25 plus 9. Then 25 can be written as 2 into 9, 18 plus 7. Similarly, 9 can be written as 1 into 7 plus 2. Then 7 can be written as 3 into 2 plus 1. And that's 2 now. 2 can be written as 2 into 1 plus 0. So we have to go on dividing until you get the remainder as 0. And last non-zero remainder will be the GCD. So now you can write GCD of 143 and 227 is 1. See this, you have got the GCD now. Now I have to express this GCD in terms of ax plus by. Okay, where a I have taken it as 227 and b I have taken it as 143. Okay, so I have to rewrite now. What I have got, the last equation, 1 is equal to 7 minus 3 into 2, right? So I can rewrite this as 7 minus 3. This 2 can be written as 9 minus 1 into 7 equal to 2, right? So the same thing, this 2 I'm rewriting it as 9 minus 1 into 7. Then the 7 here also it is there. So this is once and this is thrice. So total 4 times. 4 times 7 minus 3 times 9. Now I'm writing this 7 in terms of 25 minus 2 into 9. Okay, so 4 into 25 minus 2 into 9 minus 3 into 9. So 4 into 2 into 9 and minus 3 into 9. 4 into 25, 8, 11. So minus 11 times 9. Now I'll rewrite this 9 as 59 minus 2 into 25. So 4 into 25 minus 11 into 59 minus 2 into 25. I'll go on writing like this so that I'll get 6 into 25 minus 11 into 59. Then this 25 I'm writing it as 84 minus 84 minus 1 into 59, so that this will be 26 into 84 minus 1 into 59, 11 into 59, so that 26 into 84 minus 37 into 59. Now I'll rewrite this 59. 26 into 84 minus 37 into 143 minus 1 into 84. So this will be 26 into 84, 30 minus 37 into 84, minus minus plus. So this will be 63 into 84 minus 37 into 143. So now I'll rewrite this 84, okay, 63 into 227 minus 1 into 143 minus 37 into 143. So that this will be 63 into 227 minus 63 minus 37, so minus 100 into 143. This is same as writing, say, 1 equal to, so this is x, this is a and this is x, ax plus by, this is in this form. Okay, so I'll write here, I'm getting x as 63 and y as minus 100. This is b and this is a. X is 63 and y is minus 100. This is not the only way to express the integer 1, okay? In terms of 227 and 143, you can add and subtract these two integers and get the other equation for representing 1 in terms of products of 227 and 143. Okay, this is the small, 3-digit integer I have taken. I can even take one more. You try by yourself. Okay, I'll give one more example. GCD of 12,378 and 3054. Okay, what is the GCD of this? You try by yourself. I'll just tell you the GCD, and the GCD I'm getting it as 6. Okay, last non-zero remainder will be the GCD. To start like this, 12,378 divided by 3,054. So 4 times you can multiply this. 4, 16. 2, 6, yeah, 162, and then you write 3054. 162 into, I think 18 times you have to do, I guess so, and roughly 138 like this. You have to proceed like this. Last non-zero remainder will be 6. Therefore, GCD of this will be 6, and you have to present 6 as a linear combination of these two numbers. I'll just give you the linear combination, okay? 6 as 132 into plus 535. 305. Please try by yourself. So I'm getting like this, value of x as 132 and y as minus 535. That's once again I'm telling this is not the only way to express 6 as a linear combination of these two numbers. Okay, we can add and subtract, say by add and subtract, say 3054 and 12,378. You are getting another expression for a 6 in terms of this. Okay, adding and subtracting this. 132 for this. Okay, 132 plus 3054 into this number 12,378 plus for this minus 535, and you have to subtract this 12,378 into 3054. Okay, I have already done the calculation, that's why I'm directly writing the numbers. You check with your answers. 3186 to 12,378 plus 12,913 into 3054. So thus you are getting another number, another x and y. So this is not the only way. By adding and subtracting the numbers to the x and y, you are going to get another representation for 6 in terms of these two integers. Please go through the problem, you try by yourself and get the solution. If you have any doubts, any questions, then please comment below. Thank you.